Okay, so now let's look at an example that'll give us some insight into how this limit notation works and what it really means and what it's really describing. Okay, so you see we've got an example with a function f of x is equal to x squared minus x plus 2, and what are we asked to do? We want to estimate the function's limit as x gets closer and closer to 2. And it says to use a table of values. So here's what that means. Okay, so we're actually going to do two tables. One for the values of x which are less than 2, and one for the values of x which are greater than 2. So we're going to kind of do two separate tables and do two separate investigations. So we're going to have one column for the x values and one column for the function's output values, just like if you're doing a table of values to plot the graph of a function. Okay, so what we're going to do on the left-hand table, let's make this our table for the values of x that are less than 2. So let's pick some values of x that get closer and closer to 2, but from the left. So we'll start with 1, 1.5, 1.8, 1.9, 1.95, and then 1.999. That gets getting quite close to the number 2 now. Okay, so now if you have a calculator handy, feel free to punch these into your calculator and see what you get, and you can fill in these values on your own. But if you don't have one handy, that's okay. You can just take my word for it. I've worked these out already, and I'll tell you what they are. If you plug each of these values into the function f and work out the corresponding output values, what you're going to get is 2.75, 3.44, and then if you plug in 1.9, you're going to get 3.71. If you plug in 1.95, you'll get 3.8525, so the decimal place is getting a bit longer now. And then if you plug in 1.999, you'll get 3.997001. You can see how it might be quite tedious to work these out by hand, and it's not really that useful to do so. So if you have a calculator handy, great, punch them in. You can get this. You can check that these values are the ones you get. But if not, like I said, just take my word for it. Okay, so what's happening? Let's examine the trend. As the values of x get closer and closer to 2 from the left, what's happening to the corresponding function values? The corresponding function values, what are they doing? Well, we've got 2, 2.75, this is about 3.5, a little bit bigger, 3.85-ish, right? 3.997, now that's getting quite close to 4. So actually, in hindsight now, if we look at the trend, it's starting to look like these values are getting closer and closer to 4. But you're not sure. Right? We've only plugged in 6 values. For all we know, if we did one more value and did 1.9999, maybe you plug that in, you're going to get negative 16 or something, right? I'm not saying it's going to happen. That actually won't happen. But my point is, this table is not a full justification of this fact. It only gives you enough evidence that you can make an educated guess. So that's what we're going to do here. We're going to make a guess that the limit as x approaches 2 from the left of f of x is equal to 4. Like I said, we're not totally sure. It's not absolute, but we have a pretty good idea. We can feel pretty good about that guess. But it is just a guess. I really want to emphasize that. This is not a calculation. It's just a guess. Okay, well, let's try the same thing as x approaches 2 from the right. Let's try some values of x which are bigger than 2, but also just get closer and closer to 2. So how about this? We'll do 3, 2.5, kind of following the same pattern I did on the other side, or over here, but just on the other side of the number 2. So 2.2, 2.1, 2.01, and then 2.001. Okay, so let's plug those values in. And again, just use your calculator if you have it handy. If not, these are the values that you'd get if you did. So if you plug in 3, you end up getting 8. If you plug in 2.5, you get 5.75. If you plug in 2.2, you get 4.64. And the rest of the numbers are 4.31, 4.0301, and then 4.003001. All a neat little pattern for those last 3 numbers. But in any event, let's look at what happened. So as the value of x gets closer and closer to 2 from the right now, through values that are larger than 2, the corresponding output values of the function, they seem to be getting closer and closer to 4 as well. Like that's quite close to 4, 4.003001. So it's starting to look like a pattern is emerging here as well. We don't know for sure, right? Like I said again, if I plug in as my next x value, I plugged in 2.0001, well, maybe I'd get something else. Maybe I'd get like a negative number, or maybe I'd get like 10 or 100 or something far away from 4. It's not, you never know for sure. And even if I did plug the next number in to be sure, then I might confirm that the next number is even closer to 4. Well, then what about the number after that that's even closer, right? You can always go closer. So no matter how full your table is, you never really know for sure. But this is still good. This is enough to give us a pretty good idea, and we can safely guess, fairly safely guess, as long as we admit to ourselves that that's all it is, it's just a guess. We can guess now that the limit as x approaches 2 from the right of f of x is also 4. By the way, I want to mention something. I'll use green. These are called one-sided limits, by the way. If you write a limit notation, but you actually take your variable approaching a value just from one side, so x approaches 2 from the left, that's a one-sided. That makes this a one-sided limit. If x is approaching 2 from the right, that makes this a one-sided limit because it's only approaching 2 from one direction. Same with this one, right? This is only approaching 2 from one direction. So just want to point that out because I'll use that terminology. And then just to contrast this with the limit we were given up here, the limit as x approaches 2 of f of x, where there's no direction specified, that's I would call that a two-sided limit because you're not approaching from one direction at a time. Okay, so how would you put this all together now? Because that's the one we were asked about, right? The limit as x approaches 2 of f of x. We weren't asked for these one-sided limits, but that's the idea. You look at the one-sided limits first, and if they agree, then that means that you can safely conclude, at least with whatever level of certainty you have for these two limits, which they were just guesses. So our conclusion here is going to be a guess as well. Well, let's write it down. So since the limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the right of f of x, and they were both equal to the common value of 4, we may guess or estimate that the limit as x approaches 2. Now I'm not going to specify a direction this time because this is now the two-sided limit that we wanted to investigate. The limit as x approaches 2 of f of x is equal to 4. Okay, so this is really our answer. But again, let me emphasize, it's only a guess, right? Because we only plugged in a handful of values on either side. We don't know for sure. And no matter how many points we choose, or how long we make these tables and how nicely we draw them out and how perfect they may look, they're never going to be more than just enough to give us a guess of what the limit is. Now, there's a bit of a paradox to this. You might ask, well, why did I show you this then? Why did I even show you this method if all it does is give you a guess? Well, it's kind of a paradox because I would say that there is no better way to give yourself the intuition behind a limit and really get a chance to see what's going on than to go through this exercise maybe at least one or two times yourself with functions, right? But on the other hand, it's tedious to do. It's a lot of work. It's a lot of work to write out, and it's unreliable because, like I said, you've caught me saying this probably 10 times now. All it is a guess, so it's not reliable in the end after all that. So it's not a very practical method for calculating limits, but it is a great method for learning limits. So that's why I always like to start with one example like this. But you won't see me do any more examples like this because it's just not a practical method. One method which is a little bit better is the graphical method. If you have access to the graph of a function, or you can come up with the graph of a function, that will help a lot too. So that's how we're going to do the next example. Okay, so our next example, we've got a piecewise function. So g of t is defined to be either 1 or -1, depending on where t falls. So if t happens to be a value that's greater than or equal to 0, then g of t is equal to 1. But if t happens to be less than 0, then g of t is -1. So that's the piecewise function we're given, and we want to find the following limits. So look at what we've got here. We've got two one-sided limits. We've got the limit as t goes to 0 from the left of g of t. That's the same idea as the notation up here, right? The only difference is we're dealing with a function g of t rather than f of x, and the variable is t instead of x in our example down here. So there's nothing new here. And this is a one-sided limit. Then we've got another one-sided limit as t goes to 0 from the right of g of t. And then the two-sided limit, just the limit as t goes to 0 of g of t without specifying the direction on t. Okay, so how do we work these out? Let's start by drawing the graph. So it's fairly straightforward to sketch this graph. So we've got a t-axis and a y-axis, because this is, of course, the graph of the equation y equals g of t. So what's it going to look like? Well, the function's always either 1 or negative 1, so those are going to be the important values. Positive 1 and negative 1. So for values of t that are greater than 0, so for this range, g of t is always positive 1. So it's going to look like this. And then for the values of t that are less than 0, you're actually going to get this behavior. And it's an open dot, because if you actually plug in 0, well, that would fall under this rule, right? 0 is greater than or equal to 0. So if I actually plugged in 0, I'd get g of 0 is equal to 1. So that's why this dot is solid and this dot is empty. You don't actually include this dot. Okay, so let's work out the limits then. For part A, well, here's how you can do this. You want to find the limit as t approaches 0 from the left of the function g of t. So start with the t approaching 0 from the left. Just on the t-axis with your pen or pencil, just trace the t-axis and approach 0 from the left. And you get this path right here. And ask yourself, as you approach 0 from the left, is there a corresponding path along the graph of the function? And the answer is yes. The path would be here. The corresponding, basically the output values from the function that correspond to the points along this path would be the points over here, right? The points on the graph. So as you get closer and closer to the end of your path, ask yourself, are you approaching a point in R2? And the answer is yes, you're approaching this point here. There's no actual point on the graph there, but you'll never know that because you're only ever approaching 0 from the left. You're never going to actually get there. You're only moving closer and closer and closer and closer to 0 from the left. So the points on the curve are really only going to get closer and closer and closer to this point as well. But they are approaching a point in R2, even though it's not a point on the graph. So then finally now you'll say, okay, well if it's approaching a point in R2, what is the y-coordinate of that point? And in this case, the answer is the y-coordinate is -1. Right? That point in R2 that we're approaching, if we trace this path along the curve, its y-coordinate is -1, so that tells you what the limit is. So we can say the limit as t goes to 0 from the left of g of t is equal to -1. Okay, so that's actually nicer than plugging in a whole bunch of points and then making a guess, right? You can see that as t approaches 0 from the left, the corresponding path along the curve approaches this point. So what is its y-coordinate? Whatever it is, that's your answer. That's a pretty nice method for computing limits compared to doing all this. Although if you did a table of values, you would get confirmation at least. It would corroborate what we just did here. Okay, so that's part B. That's part A. What about part B? We want the limit as t approaches 0 from the right of g of t. Okay, well, start here. Say, okay, as t approaches 0 from the right, what does that look like? Well, go to the t-axis and approach 0 from the right. And then you're going to say, okay, what is the corresponding path along the graph of the function? Well, that would be this path here, right? So then ask yourself, okay, if I follow this path along the graph, do I approach a point in R2? And the answer is yes, you approach this point. It's different in this time because this is actually a point on the graph, but it actually doesn't matter. The path is what you care about. It's not about the destination, it's about the journey. So as t gets closer and closer to 0 from the right, the corresponding path along the curve or graph gets closer and closer to this point. So ask yourself, what is the y-coordinate? And the y-coordinate is +1 this time. So now you're going to say +1 is the limit. So that's how you can get the limit as t goes to 0 from the right of g of t. Now, lastly, part C, you want the limit as t goes to 0 of g of t. And I think my best bet is to write it down here to fit it in. I didn't leave myself enough space up here. So if I write the limit as t goes to 0 of g of t, well, this is actually the easiest one of all the three. Because once you've computed the two one-sided limits, you can just check whether they're the same or not. Like in the previous example, the two one-sided limits were the same. Right? So if the two one-sided limits are the same, then you can conclude that the two-sided limit is that same value. But if the one-sided limits are different, like this one was -1 and this one was +1, well then you just rule out this one entirely. This one doesn't exist. There is no sensible value to assign to the limit of g of t as t goes to 0. So we just say this does not exist. In fact, I shouldn't even have wrote that equal sign. I'll scratch this out and we'll just say does not exist. right? And you can abbreviate that with DNE, which is what you'll typically do. Just stands for does not exist, because lots of limits don't exist, and we'll be working with them a lot. So if someone says find a limit and it turns out that the limit doesn't exist, that's still the same as finding the limit. Or sometimes the language will be estimate the limit or investigate the limit. You'll see lots of those languages be thrown around, or calculate the limit. Couple remarks to finish this page off. This is really just to hit home the ideas we've already kind of highlighted here. Let's look at the first remark. Whenever the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of f of x. So in other words, whenever your two one-sided limits are not equal, you immediately conclude that the two-sided limit, because that's what this is, limit as x approaches a of f of x, does not exist. Right? So you immediately say that this does not exist. I'll just write this out in its entirety one last time, but usually I'll just use the acronym DNE for does not exist. Okay, and the other remark says that, well, when you're calculating a limit, and this goes for one-sided limits as well, but I just happen to have stated it in the case with a two-sided limit, but whenever you're calculating a limit at all, as x, let's say as x approaches a, you never actually care what happens to the function when you plug in x equals a. That is absolutely irrelevant. Right? You only care what happens to the values of the function as x gets closer and closer to a. That's the whole point of a limit. If we wanted to know what the function did at the point a, we would just plug it into the function and be done with it. We wouldn't have gone into any of this conversation about approaching or converging or getting arbitrarily close to something. All that discussion would be moot. So we don't actually care what happens when you plug in the point a. We only care what happens to the function values when the values of x get close to a. So an example of that is this point was empty, right? When we were calculating the limit as t goes to 0 from the left of g of t, we said, okay, take your pen, approach the value of 0 from the left, find the corresponding point on the curve, and ask yourself, which point in R2 are you approaching, if any? And the answer was this point here, the one with a t coordinate of 0 and a y coordinate of -1. That's the point we were approaching. It's not a point on the graph. We don't care if it's a point on the graph. That's what we mean when we say we don't care what happens at the point x equals a. Or in this case, we didn't care what happens at t equals 0. We just care what happens as you get close to t equals 0. So in this case, it turns out that the values were getting close to this point. It had a y coordinate of -1, so that's what we took to be our answer. But if we flip this, so the solid dot was moved down here, and this was solid and this was open, so you basically fiddle with these inequalities a bit to make that happen, it wouldn't have changed any of the outcomes of those limits. It wouldn't have changed, it wouldn't have changed any of the values of these limits at all. Okay, so that's our second remark.